In this video, I'm going to show you how exactly language models work. So sit tight because attention is all you need. Have you ever wondered how your phone is able to understand what you're saying and respond back intelligently, or how chatbots are able to have conversations with you? Well, behind all these magical experiences lie language models, complex algorithms that enable machines to process and generate human language. Let's start with the basics. What exactly is a language model? Essentially, it is a statistical program that analyzes patterns in massive amounts of text data. Just like we pick up language skills from reading books, language models gain an understanding of language from reading tons of text. Using this knowledge, they can predict the probability of a word appearing next given the previous words. For example, if the model sees the phrase "I love to eat," from all probable words, it chooses the one with the highest probability based on its trained data, for example, food, as the predicted next word. Have you noticed that intuitively you almost know the next word when you read a sentence? Predicting the next word is the basis of all language models. To see how this prediction evolved, let's take a look at early language models or rule-based algorithms. In the rule-based architecture, all the rules of a language were given to these deterministic algorithms, which in turn were used to produce a human-like piece of language, for example, a sentence. Just as you can code the rules of a game to an algorithm, you can code the rules of a language, mainly grammar and syntax, as well as the rules of forming words or morphology, and expect that with a limited amount of data, the algorithm would be able to produce natural language as spoken by humans. But there were multiple major problems with this model. For one thing, the algorithm could not produce nor understand the complex relationship between words and ideas, such as metaphor, sarcasm, implicit language, and so on, as appear in literary, philosophical, and any type of language that requires imagination and contextual understanding, simply because there are no rules for them to code. Another major problem with the rule-based models was that during the training process, a human rater had to judge the accuracy of the data, for example, the accuracy of part-of-speech tags, and assign errors to wrong cases to be corrected for the model to be able to produce correct outputs. This, as you can see, is a very time-consuming task, even for judging the relevance and sufficiency of simple question answering and parsing data. So computational linguists figured out a way to overcome these challenges. Here's when statistical language models were born, which are the foundation of model language models. Instead of defining a set of rules, the statistical language models use a probabilistic algorithm to assign probabilities to each word occurring based on the previous word. We can use the chain rule to find the probability of the next word as the product of probabilities of words in a sequence of words. For example, the probability of the first word, the probability of the second word given the first word, and so on, until we get the conditional probability of the nth word given all previous words. This led to an outstanding improvement in natural language processing or the processing of human language by way of n-grams or a sequence of n words using relevant trained data. The idea is to find how many times a given sequence of words occurs in the training data and use this information as the basis to predict the next word. As significant as this step was in the evolution of language models, this type of model still lacked broader contextual understanding and meaning making. Then came the most impactful jump in this evolution, which was the use of neural networks for processing the complex relationships in the data. Even though the concept of neural networks emerged in the 1940s to model how the human brain and neurons process information, with the works of scientists such as Baron McCulloch and Donald Hebb, it was not until the late 50s that an actual algorithm for it was designed in Stanford. The earliest neural network algorithm was called Multiple Adaptive Linear Elements, or Madeline, to predict the next bit in streaming bits from a phone line. This was an early example of a feed-forward neural network. In our example of word sequences, the most simplistic explanation of a feed-forward network is that during the training process, any sequence of words can be given values as input to the algorithm. The model then multiplies each input value by a weight it assigns to its connections to mark the importance of each in predicting the next word. The sum of weights makes the prediction for each node, and so forth, until the final prediction or the predicted word. From mid-70s till mid-90s, neural networks witnessed the idea of backpropagation. In their cores, most neural networks use gradient descent to train the data and to compute the error value in the entire training set. The error is the difference between predicted and observed values, for example, for the prediction of each next word in a sequence. Ideally, this error value would be as close to zero as possible, making the prediction as accurate as possible. In a feed-forward network, the input only goes forward through the network towards the output to compute the error and output a prediction. In the backpropagation method, the error values can go backwards from the output to the input to adjust the weights by registering the difference between the prediction and the actual result based on the training data. This allows the system to reduce the error by learning, for example, by adjusting the weight values given to each possible choice of word as the next word in the sequence, and improving the accuracy of the final predicted word. The idea behind backpropagation is to use the training data set where we already know which word occurs next in a sequence to train the algorithm by letting the error value between any possible choice of word and the actual word that we know of go back, and the choice corrects or updates itself until the choice of the next word matches the actual output or come as close as possible to it. In this process, the weights given for any choice of word in the sequence are adjusted to the most accurate value possible. Once the algorithm is trained with the best weights, it can predict the next word in any other given sequence of words. As significant as the backpropagation models are in increasing the accuracy of the predicted words, they have a major problem. They are processor intensive because of no possibility for parallel processing of word sequences. What perhaps transformed the landscape of artificial intelligence was the concept of transformers, which helps the models to better understand contextual information. The transformer architecture, which was proposed in the 2017 seminal paper Attention is All You Need, allows the models to assess the importance of each word in a sequence. In other words, it assesses which word deserves more attention in each context. It identifies the distance between words that influence each other. This attention mechanism processes relevant input words and masks other information in words that are not very relevant. Owing to the parallel processing, transformers have this attention mechanism which lets them learn from complex relationships between words and, by extension, ideas in natural languages. Transformer architecture includes an encoder and a decoder unit. The encoder unit has 6 layers, each with 2 sublayers. The first sublayer is a multi-head mechanism which generates multiple parallel outputs. The second sublayer is a feed-forward network. In this sublayer, the input data, for example, a sequence of some words, enters 6 layers of encoders where each layer uses its own weight and bias parameters, for example, the weight or importance given to each word in a sequence. The encoder unit takes all the words in a sequence without paying attention to their order or position in the sequence. Instead, it encodes their positions in a vector for itself so that later on it can retrieve their positions. The decoder unit has 6 layers with functions, each with 3 sublayers. The first sublayer receives the output generated from the encoder, then provides positional information about the words, and applies a self-attention mechanism where only the previous words in a sequence up to a point are considered. The second sublayer receives both the output from the encoder unit as well as previous decoder layers. This allows the system to pay attention to every word, both regarding and regardless of their positions in a sentence. In the third sublayer, another feed-forward network is applied to find the final predicted word based on the information from the previous steps. Therefore, the decoder unit converts the encodings back to probabilities, which are in turn used to select the output words or the next word in the sequence. Since the transformer neural networks put the importance of any token from the input in the context of other input tokens, they are great options not only for natural language processing, but also for the processing of any sequences of data, such as genomic sequence and time series data. Perhaps that's the reason that transformer neural network replaced other architectures such as recurrent neural networks, short-term memory, and gated recurrent networks so fast. Large language models are direct results of the transformer neural networks using large sets of training data, making these models superior in contextual understanding. An example of these large language models, or LLMs, is GPT, or Generative Pre-trained Transformer, which is implemented in various versions of ChatGPT. It uses this contextual understanding to produce meaningful and coherent conversations just like humans. Other notable large language models are PaLM, or Passphrase Language Model by Google AI, BERT, or bidirectional encoder representations by Google Brain, and LLAMA by Meta. Often billions of parameters are tuned in these LLMs, which makes them adapt to specific tasks such as text generation, question answering, or sentiment analysis. In the next video, I will explain how exactly language models process natural language with some common NLP tasks. But before you go, let me share something interesting with you. I asked the Bard chatbot, how many calories does it take a person to click on something online? As you can see the full answer on the screen, perhaps just your click on the like and subscribe buttons of this video would cost you less than 1 calorie, but it keeps feeding the algorithm for this channel to grow.